This meeting is being recorded.
To unmute. Good.
Hello, everyone. Hope you can hear me, right?
Yes.
Oh, okay.
Yeah, thank you, Christian.
Yeah, this is 11 a.m. West African time, and we're here again for our next seminar, which is the Fast4Future seminar, April seminar. Today we have a presenter, Dr. Piotr Kowalczyk-Szymanski, who is an assistant professor at University of Wrocław in Poland and a postdoctoral fellow at University of Leeds in Belgium. He obtained his PhD in stellar astrophysics and will be talking to us today about eccentric ellipsoidal variables. Piotr, the floor is yours.
Thank you very much, Christian. And first of all, I would like to thank you to all of you for the very kind invitation I get. So this is my first time when I can virtually be invited to the Africa generally. So this is my first time in Africa, let us say. And yes, today my seminar, I would like to say a few words about the evolution or general about the eccentric ellipsoidal variables. So this story will have a lot of context, a lot of threads during my speech. I will not only talk about binary systems, focusing on the eccentric ones, but I would like to also mention tidally excited oscillations. These are very special type of oscillations that we might have in stars in general, and also about collapsing tidal waves, because not all of the tidal interactions that we may have in binary systems are only linear ones. So some of them are so severe, are so extreme, that we may expect to observe some non-linearities in their behavior. Okay, so I will start my presentation with a short motivation and introduction of scientific context. So, because I don't know exactly what kind of audience I might have now before your screens, let me begin with the multiplicity of main sequence stars. If you see this irritating small thing, I will move it here. Now you should see the unobscured view of the entire slide. Okay, so that's one of the most recent diagrams, which is summarizing the multiplicity fraction among main sequence stars. As you may see, here on the x-axis, we have the mass of the primary component in such a binary system. And on the y-axis, we have multiplicity fraction. So this fraction expressed in percents tells you basically what is the percentage of stars which have at least one companion, so at least one additional star which is revolving around it in a binary system, in a tertiary system, or even higher order multiple systems. As you may see, there is the rising trend. So if we will focus our attention on very low mass stars, so stars with masses which are well below 0.1 solar masses, we see that, okay, roughly 20% of these stars are residing in binary systems. But moving to larger masses, and especially to stars of spectral types O and B, we may see that almost 80 or even 100% of these massive stars are contained in binary systems. So this is a very important thing when we are discussing the evolution or characteristics of massive stars, because we may be almost 100% sure that they are always residing in a binary systems or even higher order multiplicity systems. That's why the evolution is so complicated. That's why the analysis of observational data is very difficult, because we may no longer assume that by observing a massive star, we see just a single star, which is well isolated out of any companions it may have. That's why it's also so interesting to focus on these binary systems, because we have, plenty of evolutionary scenarios. And in the next slide, I would like to show some of these scenarios. So this awfully overwhelming figure you may now see in this slide is a very brief summary of the main evolutionary scenarios you may encounter when we have a binary system. So let us imagine we have a binary system, and depending on the initial conditions of this binary system, we may observe a plethora of different evolutionary scenarios. So the first division you may see here, I know that the size of letters is very small compared to the size of the slide. I'm sorry for that. I couldn't find, a better picture. But the main division you may see here is with respect to the size of the initial binary orbit. So if the orbit is very wide, such a binary system is evolving almost like it was, containing just effectively single stars. But if you have massive binary systems in relatively close orbits, you may see we have plenty of evolutionary scenarios, and almost all of them are ending with very tight configurations. So now with these red arrows, you may see they popped up in the slide. I highlighted such a places where the final end product of the binary evolution is a pair of, is a double black hole, or a pair of two compact objects, like black hole plus neutron star, or black hole plus, one of the white dwarfs. Yes, and as you may see, these systems are very interesting in the contemporary astrophysics, of course, because they are linked to supernovae, they are linked to gravitational waves, and the gravitational wave astronomy is very, very rapidly developing currently. That's why studying especially massive and tight binary systems is one of the most, one of the most hot topics in modern astrophysics. Of course, there is one complication we might have, because from the perspective of gravitational wave astronomy, so the astronomy which is focused on the end products of these binary systems, to simulate them and to predict the population quite accurately, we need to be able to describe tidal interactions during the initial stages of their evolution. So with these green arrows, I highlighted such evolutionary phases when tidal interactions are very important when you would like to simulate the evolution of binary systems. As you may see, these green arrows are located mainly above the red ones. So it suggests that simulating the population of double black holes or double neutron stars require the knowledge, quite delicate and dedicated knowledge, about tidal interactions in binary systems. And that's why the importance of tidal effects is so important. And that's why in my studies I was focused in eccentric binary systems and many types of tidal interactions that we may encounter, especially in the massive ones. So, starting the story about heartbeat systems, about eccentric ellipsoidal variables, this is a set of free simulations I generated for you in the Phoebe software. As you may see, we have a twin binary system consisting of two identical A-type stars. They are placed in a slightly eccentric orbit, which is viewed from different inclination angles. So both the argument of periastron and inclination angle of the orbit is different in each row of this animation. The color scale shows you the distribution of local effective temperature, while the set of panels which are located on the right-hand side shows you almost in the live view what kind of light curve we may expect due to this orbital motion in the binary system. As you may see, almost always we have a quite brief pulse-like feature in the light curve, which sometimes resembles the electrocardiogram signal, like in the medical sciences or in a doctor, if you're making such a diagnosis. And because of this correspondence, I mean, because of the shape, this kind of binary systems are sometimes called as heartbeat stars, because we have this heartbeat signal which is present in the light curve. But this is one of their names. And this figure, which is the artistic view, shows you the visualization of the periastron encounter. So when the both components in the binary systems are located very close to each other, they are deforming each other. So we have the ellipsoidal variability in such a system, but we also have the mutual irradiation of both stars. So because the distance between components is so close, and obviously both stars are radiating energy, as radiating photons from their surfaces, we have the mutual irradiation. So both surfaces are redistributing the heat which is emanating into their surfaces. We also have some small additional signals which is originating from Doppler beaming and Doppler boosting, but in most cases this signal is quite a minor issue compared to the former two ones I mentioned. And depending on the orbital inclination and argument of periastron, you may see that the shape of these light curves varies significantly. So that's why if you have just the light curve, it may be the light curve derived from ground-based observations. It may also be a light curve from, for instance, TESS satellite, yes, or Kepler data, Kepler data. You may derive orbital parameters based solely on the light curve. Of course, sometimes it's quite difficult, but generally for heartbeat stars, even if you don't have radial velocity data, you may model them and say something about their inclinations just by looking at the morphology of the light curve. So the previous slides were just about heartbeat phenomenon, let us say. But there is also some another phenomenon which is completely different from equilibrium tides I showed you in the previous slides. And this animation shows you another behavior which is called tidally excited oscillations. So this is the manifestation of dynamical tides. I know that the simulation is quite complicated, so let me begin with the explanation of the central part of the figure we see here. So every time where the secondary companion is approaching the primary one, we see that it's trying to push a little bit the surface of the primary star. And this small push is the dynamical tide. So basically what the star is trying to do after the periastron passage, it is trying to regain the equilibrium, the hydrostatic equilibrium, which was destroyed because of the close periastron event. And this kind of disturbance may excite a lot of oscillation mode inside the star, which are called tidally excited oscillations. So normally, without the presence of the secondary companion, they won't be visible because we don't have a forcing body. But because the secondary companion is once per every orbital cycle is trying to push a little bit the volume of our star and is trying to distort the volume of the star, these oscillations may be excited. The set of these panels shows you the decomposition of dynamical tides into separate oscillation modes. All of them are very different in terms of frequency, also in terms of their geometry. As you may see, there is a plenty of them. So every periastron passage will excite a set of tidally excited oscillations, and they may be seen in the light curve as the variation which is located outside the periastron passage. So this small insert in the animation shows you the flux variations we observe from Earth distance. And this phase in the central part of the graph is corresponding to the periastron passage. So this pulse is the heartbeat. This is due to equilibrium tide in general, but the variation of flux, which is visible outside periastron passage, is due to tidally excited oscillations. And these oscillations are very important from the evolutionary point of view because they may modify parameters of the orbit. So usually when you have a binary system, the only contribution to tides is due to equilibrium tides. So this is the tidal friction. This is the damping of the radiative damping of waves in the atmosphere. But if you will include tidally excited oscillations, they will also contribute to the evolution of orbital parameters in such a system. And actually, they are quite important ones when it comes to the dissipation. So that's why for the next slides, I would like to slightly focus on this topic. So on the impact of tidally excited oscillations on the evolution of different orbital parameters. And probably naively, most of us would expect that over the time, the orbital period and the eccentricity of the binary system would evolve in such a way I'm showing you right now in the slide. So there is a famous work, the seminal work by Zhang. This is almost, this is a boss, let us say, when it comes to the description of tidal interactions in binary systems. And according to Zhang's formula, the orbital period generally should decrease over the time because the system is getting tighter and tighter due to tides. Yes, so it's reducing the size of the orbit. That's why the orbital period is getting lower. And when it comes to the eccentricity, once again, because of the tidal interactions, we should expect that the eccentricity will be damped. Yes, so the system generally would become more circular over the time. And all of these changes should be smooth, as I also highlighted in the picture. So this is the, let us say, naive view when we do not account for the impact of tidally excited oscillations. However, there are some papers in the literature, some of them are even quite old, some of them are more recent ones, which are trying to simulate the evolution of binary systems with the addition of these tidally excited oscillations. And if you will you will just switch on this additional source of tidal interactions in your code, in the evolutionary codes, which are trying to integrate the evolution of binary systems, you may see that the situation is completely different. So first of all, let us focus our attention on the set of these slides, of these panels. So on the left-hand side, these panels are showing you the results for the experiment performed by Vite and Savonier around 20 years ago for a toy problem. So this toy binary system is consisting of two 10 solar masses main sequence stars. They are rigidly rotating. And as you may see, their evolution is integrated over the time, which is counted in millions of years, and different values, different quantities tracing their evolution is present in this diagram. So, for instance, this black solid curve shows you the evolution of orbital period over a time. As you may see, this evolution is no longer smooth. So there are some parts where orbital evolution is decreasing, like we might expect from the Zhang's theory, but there are also some step-like structures which are quite non-monotonic in this curve, and there are even some changes with the increasing rotational period. And this is surprising, yes, because this is something completely different we might expect from the Zhang's formulation, which should be smooth, yes, and only with decreasing periods. So here we have a significant change. When it comes to the eccentricity, once again, it is marked with the solid line. The eccentricity is more or less decreasing over the time, but we also see this stair-like or step-like structure in this data. So there are some moments in the evolution where the characteristic timescale of reducing both orbital period, eccentricity, rotation period also of both stellar components is completely different and is varying significantly over time. So for instance, here, when we have this very rapid decrease in the orbital period, this is the phase of the evolution where we have one of the TOs, so one of the tidally excited mode, which is contributing to the accelerating tidal evolution of the system. Then, when we are out of the resonance, so we have no longer the contribution of tidally excited oscillation, we see just the smooth changes. And once again, every time when you have a sudden drop, when you have a sudden decrease or increase in the orbital, one of the orbital parameters, we may expect that this is due to the contribution of tidally excited oscillations. So from the observational point of view, including tidally excited oscillations is very important, for instance, to explain the observed distribution of eccentricities and orbital periods for solar-like and intermediate mass stars in binary systems. This is the typical diagram which is usually constructed for binary systems, where you just plot the orbital period and eccentricity, and usually what you should see is the decrease of eccentricity when we move towards closer, tighter orbital configurations. And of course, for very short period binary stars, as you may see, we have only circular orbits. But when we have longer orbital periods, we may see that some of these binary systems have some non-zero eccentricities. And if we will account only for equilibrium tides, so we will completely neglect the effect of tidally excited oscillations, we should expect that the envelope, the so-called envelope of this distribution, should be located somewhere there, which is indicated by this dotted line. But only after accounting for resonance locking, so for the phenomenon which is corresponding to the presence of tidally excited oscillations, we are able to explain this kind of observed distribution. So tidally excited oscillations and generally dynamical tides are very important ingredient when it comes to the simulation of evolution of binary systems. Okay, now let us focus a little bit on the observational characteristic of the heartbeat signal, which may be observed in different, ground-based surveys or photometric surveys, like the TESS satellite, for instance. These are results from one of my works when we were trying to hunt some of the heartbeat stars in the TESS data, yeah, maybe we should just focus our attention on the set of these panels. So these are observational examples of different heartbeat systems which contain intermediate mass or massive components. As you may see, they are summarizing the changes in the normalized flux over the orbital phase. Every time there is this sudden, pulse or a heartbeat in the light curve. Sometimes it's quite delicate. It's a very subtle effect. As you may see, the amplitude of these changes expressed in parts per thousand. So to translate it to percentage, it will be around 1 promille. Yes, it will be 0.1%. So we see the changes in the total flux which is coming to us from these stars on a level of just 1 or sometimes several ppts. This is a very subtle effect. Still, it's detectable in from spaceborne observations. Depending on the eccentricity, the shape of this pulse may be narrow or quite broad. So if the system is of significant eccentricity, like this one, for instance, we may see that the signal is concentrated just around the periastron passage. But if we have a case which is of quite small eccentricity, like for instance, the light curve of Theta Carinae, we may see that the signal is distributed almost over the entire range of orbital phase. So the narrowness, or generally the width of the signal, is corresponding directly to the eccentricity of the system. So that's why observing heartbeat stars may also tells you something for free about the eccentricity of the system. Yeah, this plot, I think we will skip this one because it's quite difficult to explain it in total and in detail. Yeah, when it comes to the tidally excited oscillations, we may see some examples here. So this one is a very nice example. HD 150013 shows very nice division into the heartbeat signal, which is overplotted here as the blue line, a darker blue line. And if you will subtract this signal from the light curve, you may notice that in the residuals, there is something additional. And this additional variability is also periodic. So yeah, and this periodic variability is exactly because of the tidally excited oscillations. So probably what is happening in this system is the situation where you not only have the equilibrium tides, so the tidal bulge, which is arising due to the presence of the secondary component every periastron passage, when it's trying to collapse back to the stellar surface, so the primary component is trying to regain the equilibrium once more. This equilibrium is not regained totally. So one of the modes is excited. And that's why outside the periastron passage, which is located around the phase 0.5, you still may see some oscillations. These oscillations are due to dynamical tides. Okay, so spotting them just by looking at the residuals is quite easy in this case, but we may imagine that we would like to be very precise and we would expect some very small amplitude changes. So then we can turn on the Fourier-based analysis, and in the Fourier spectra, where here we have the frequency of the oscillations expressed in cycles per day, and the amplitude in PPTs, we may see that if you will calculate the Fourier periodogram on the residuals, so on this light curve, you may see that we have some excess signal which is located exactly at the integer multiples of the orbital frequency. And yeah, so for instance, we have a TO which corresponds to 7 times orbital frequency, 9 times the orbital frequency, and also there is some small addition from TO located at 18 times orbital frequency. So we have in total 3 tidally excited oscillations, which are hidden in this signal of this massive heartbeat system. Sometimes the situation may be even more complex. So this is the Theta 1 Crucis, another massive heartbeat systems. As you may see, the heartbeat signal is quite smooth. So after subtracting this signal, we are left with the residuals. And once again, calculating the Fourier periodogram on these residuals, we may see that we have a lot of tidally excited oscillations, which are highlighted with blue vertical lines. So here we have at least, I'm not good at counting it now, but I think we have around 10, maybe 8 tidally excited oscillations, which are hidden in the light curve of this binary system. What's very interesting is that for some of heartbeat systems, we may also observe intrinsic self-excited oscillations. So in these plots, as you may see, after removing both heartbeat signal and tidally excited oscillations, we still some additional periodic signals, probably due to pulsations, which are present in the Fourierograms. So yeah, and that's an interesting question, because usually when we imagine stellar oscillations, which are self-excited oscillations, we are thinking about the star which is isolated, and or at least the star which is not significantly tidally is distorted. But because here in eccentric binary systems we have a distortion which is evolving over time, we may expect that the self-excited oscillations will be suppressed, because the geometry of the star is distorted, and moreover this distortion is evolving over time. Yes, so naively we may expect that due to the presence of the secondary companion, due to these tidal interactions, we shouldn't expect large amplitude self-excited oscillations. And it's very interesting to see them actually. And even we have also a separate case of tidally tilted pulsators. This is another story, but it's worth mentioning it now, that there are some stars where the axis of pulsations, of self-excited pulsations, is pointing towards the secondary companion. So tides may do very weird things with self-excited oscillations. That's why I would like to mention this context also when we are talking about heartbeat systems. Okay, but spotting heartbeat stars only in test data or generally in spaceborne observatories is not the only possibility to detect them. I was also working on detection of heartbeat systems in ground-based observations, and in Poland we have, I believe, one of the most famous Polish photometric survey is the optical gravitational lensing experiment, OGL, as the abbreviation says, which is the very long-lasting, over almost 30 years project, which is observing mainly the galactic bulge and galactic disk, also small and large Magellanic clouds connected by the Magellanic Bridge. That's why here you see all of these OGL fields marked in the figure. With this ground-based data, we can also detect a lot of heartbeat systems. However, because of the observational bias, with this data, we are able only to detect binary systems and heartbeat stars with the largest amplitude. As you saw in the previous slides, many heartbeat systems have amplitudes of the order of 1 ppt, 10 ppts. Of course, this is very small compared to the photometric quality of OGL data. So with OGL, we are just able to spot amplitude variations, which are the largest one, which are of the order of 0.1 magnitude. So even sometimes the extreme cases. And after analyzing these light curves, which are spanning almost 30 years, Marcin Wrona, with collaborators with me, with Milena Ratajczak and many others, we were able to detect almost 1,000 heartbeat systems in this data. Their example light curves are shown here. As you may see, we have generally two populations of binary systems. Some of them have very relatively long orbital periods. These orbital periods are always overplotted here. Yes, they are given in the panels. So above 100 days, sometimes it's even around 500 days. So generally of the order of 1 year. These systems are composed of evolved red giant and a secondary component, which is probably a main sequence star. We also have another population of systems with main sequence stars. Here you may see the impact of the eccentricity. This is something very interesting. So starting from very low eccentricity and moving to larger ones, we see how the pulse of the heartbeat signal is getting narrower and narrower. And the same conclusions are said once again in the color magnitude diagram. When it comes to the typical amplitude in the I band we may see in the auger data, as you may see, it's typically of the order of 0.1 magnitude. Sometimes it's even close to 1 magnitude. So these systems are truly the systems with the most severe, the most significant binary, tidal interactions we may observe in nature. Yeah, we were also able to spot some TOs, tidally excited oscillations, in some of these heartbeat systems. This is one of the most beautiful examples we have in a sample. So this drop in brightness you may see here in the light curve is not due to eclipse. This is not the impact of the eclipse, although it may mimic eclipses. It's because of the heartbeat. So depending on the configuration of the orbit, sometimes the heartbeat signal may mimic also eclipses. And outside the periastron passage, once again, you may see the signal, which is the periodic variation, which is phasing very well with the orbital period. So this tells you that we have at least 3 tidally excited oscillations in this case, in a binary system which is consisting of a red giant and a main sequence star. So tidally excited oscillations are not only excited in systems which are on the main sequence, they are also excited in heartbeat systems, which are very evolved ones, actually. And this is interesting. This is interesting because of the asteroseismic point of view. I know it may be not known to all of you because asteroseismology is very narrow and very detailed field in the stellar astrophysics, but moving from the main sequence to the red giant branch, there is also a significant change when it comes to the nature of stellar oscillations. So on the main sequence, we have mainly gravity and pressure modes, while on the RGB phase of evolution, we have the so-called mixed modes. So almost all oscillation modes in red giants have this mixed nature of gravity modes in the interior and the pressure character in the envelope. That's why it's so interesting to observe this kind of forced oscillations in red giants. Yeah, and in the world of heartbeat systems, there is one particularly interesting example, which is called extreme heartbeat by Jaya Singh and his collaborators. So this is a binary system which is consisting of slightly evolved, generally, okay, let us say evolved blue supergiants. And the secondary companion is most likely the massive main sequence star. As you may see here, this is the light curve, the test light curve of this system. So once again, every 30 days, you see this nice pulse in brightness, which is due to equilibrium tight in the system. So this is the heartbeat. And then you see some variations outside the periastron passage. After the careful analysis, we were able to show that we have several TOs in this system, but we also have a very interesting TO, which is corresponding, and dum-da-dum, this TO corresponds to 230 times orbital frequency. So this is a tidally excited oscillations, which is corresponding to the highest known multiple of the orbital frequency. I mean, it's very mysterious how it is possible to induce such a TO in this system. And also, if you will see what is the amplitude of this effect near the periastron, is the extreme one. So you have to believe me now, because it's quite difficult to say it from the ordinate axis, but the amplitude of this variation in flux is of the order of 0.4 magnitudes. So this is the largest variation ever known in the massive binary systems due to only tidal interactions. Yeah, that's the extreme case. The very interesting ones. Another thing which is very interesting about tidally excited oscillations in this extreme heartbeat is that they are changing their amplitudes over time. And that's once again something very interesting because, generally, tidally excited oscillations, as the name suggests, they are excited every periastron passage. So every 30 days in this system, when the secondary companion is passing the periapsis point, these oscillations are induced. Yes, so the stellar surface is pushed away, is trying to regain equilibrium. So every 30 days, these tidally excited oscillations are being pumped up, are constantly being pumped up, and that's why it's so mysterious why we see that their amplitudes are varying. This comparison is especially important. So if you will extract the light curve of this system from the first year of test observations, you may see we have nice variation as outside the periastron passage corresponding to TOs, but after almost 1 year, if you will extract the light curve from the third year of test observations, you may notice that the shape of the light curve changed, dramatically outside periastron passage. So the poles near the periastron is the same. Okay, this shape is almost exactly the same, but the variability which is located outside periastron passage is completely different. And this is because the amplitudes of TOs changed over that time. So after 1 year, something happened, and now these oscillations are acting in a different way. The same conclusion may be seen in these plots. We are showing you the evolution of amplitudes and also frequencies of these oscillations. So also the frequencies are changing in this system. Let me skip this slide because I assume I have around 24 minutes. Am I right? Yes, for my talk, or 1 hour?
Actually, the 24 includes time for questioning, so you have
Okay.
about
So
9 minutes
yeah.
left.
So
Yeah.
okay. So I have to skip some of my slides. I'm very sorry for doing this. But let me in the end, let me just mention that this one very interesting phenomenon. So the extreme case of tidal interactions. Sometimes in the literature, you may encounter the term which is called a heartbreak system, not the heartbeat system, but heartbreak system. This is when the periastron encounter is very close. So the simulation you may now see here, I will just try to restart it once again. Let's imagine we have a very close encounter in the periastron, and the tidal interaction is so severe that even some portion of the matter is ejected away from the star. So this kind of systems are very extreme, very rare, because the characteristic time scale and the characteristic, circularization time scale for them is very, very short. So now one of the most interesting things I would like to do in my work is spotting as many of these systems in the observational data. So discovering such evolved system when the secondary companion is almost, grazing the surface of the red giant. And the red giant is so severely distorted that a portion of matter is, ejected every periastron passage we might have. Okay, with this conclusion, I would like to end. So I have a lot of slides, as you may see, but now I would like to thank you for your attention. And if you have any questions, please do not hesitate to ask them now. Thank you.
Thank you very much, Piotr, for the very nice talk. Now it's time for questions. I will take up. So if you have any question, you may raise your hand. Once I point to you, go on with the question. While we are waiting for questions, we have 2 questions in the chat. The first one, that's the question by Aman Harun. The first question, probably he joined a little late, is asking if there are 3 star systems.
Could you please, Christian, repeat once again the question?
Okay. the first question is the person is asking if there are three-star systems.
You mean triple systems?
Yeah, that's what he means.
Exactly. Yes. Yes. So generally, yes, we have a lot of triple systems, and currently, if you would like to supplement the first figure I showed you with including only the triple or generally higher order multiple systems, we see a similar trend. So let us imagine that on this axis, we would plot not the multiplicity fraction, but the number of systems with at least 3 stars which are gravitationally bound. So 3 stars, 4 stars, 5 stars in a system, and many more, as almost as many as you wish. So generally, for such a quantity, we see a similar trend. But this trend is even more steeply rising towards higher masses. So the triple system and quadruple systems are almost only observed for massive stars. There are some examples also for less massive stars like solar mass stars or intermediate ones, but they are quite rare. However, for massive stars, so let us say from 10 masses towards the higher masses, we see a lot of triple and quadruple systems. Almost all of them are, of course, hierarchical ones. So the one system, we have an inner system which is quite close, and there is a tertiary companion which is located quite far away from the inner system. Okay, so this kind of configurations, yes, they are possible. They are quite abundant, and they can be stable from dynamical point of view for millions of years. Yeah, I hope this answers your question.
Okay, thank you.
You're
Then
welcome.
he had a follow-up question again. What is eccentricity of star in binary systems?
Yeah, so the eccentricity, yeah, we may see them, for instance, there. Let me show you once again. Some observational examples, of course. Almost the entire range of values is possible. So, for instance, for ogle Harbit stars, if I will show you once again this plot where you see observational examples with different values of eccentricity, as you may see, we are starting with a value which is very close to 0. So this is an orbital configuration which resembles a circle, effectively. But we also see some examples which are significantly less abundant in a sample, but still the orbits may have eccentricities as high as 0.8, 0.9 even. And there is this smooth transition towards parabolic and hyperbolic orbits. So yeah, I think the highest orbital eccentricity we currently see for a heartbeat star is around 0.85, let us say. Higher eccentricities are much harder to spot, much harder to observe and detect, because when you have an eccentricity which is coming very close to 1, so let us say is from the regime between 0.9 and 1, uh, also the orbital periods are starting to being very long. And that's why it's so difficult to spot this system, because with very long orbital periods, we need very long baselines to observe them. And this is the reason why we don't know many of such systems. And there is also a question if a system is gravitationally bound or not, because when we are coming close to the eccentricity, which is, very close to 1, there is always a question if this system is truly a gravitationally bound system, or maybe the error on the eccentricity is high enough that we are not able to discriminate between gravitationally bound and parabolic orbits. So that's always a question. But I think if I would like to be, to be honest, the highest eccentricity we see now for heartbeat system is at 0.85. Yeah.
Okay, thank you. Let me ask a question. Because we understand that one of the main effects of tides is tidal secularization of systems, in which eccentric orbits get secularized and they become secular orbits. So, but what I want to ask is whether we still expect tidal, maybe some interactions in a system that has secular orbits.
Which are completely circular, yeah?
Yeah, do we still expect some kind of interaction, sometimes maybe tidal or any form of interaction in a system that is already completely secularized?
Yes. Yeah, this is very interesting and very good question, actually. So generally, yes. The tidal interactions are completely switched off if we have a system which is circular, and if the system is also synchronized. So let us imagine we have a system with circular orbit. That's the first thing. Another thing, we have the rotation period of both components, which is exactly equal to the orbital period. That's the second thing. And the last thing, we also have both axes of the rotation to be exactly perpendicular to the orbital plane. So with these three criteria, with these three conditions, okay, we may be almost 100% sure that we don't have any kind of tidal interactions which are further modifying the orbit of such a system. But and there is but always. So if we have a differential rotation in the interior of stars, we may still expect some kind of tidal interaction. So let's imagine that only the surface of a star is rotating synchronously. So the orbit is completely circular. The rotational axis is exactly perpendicular to the orbital plane. But inside the star, in the deep interior, we have the differential rotation. And of course, if we have a differential rotation, we may no longer stay completely synchronized with the orbit. So we still will observe some impact of tides in such a system. And furthermore, we will always also observe some kind of both dynamical tides and equilibrium tides if we don't have this alignment between the rotational axis and the plane of the orbit. So let's imagine the situation that's okay. The rotational period is exactly equal to the orbital one, but one of the components, at least, is somehow tilted to the orbital plane. Okay, so in the extreme case, we may imagine that we have an Uranus like star in the orbital system. Yeah, so the rotational axis is significantly tilted with respect to the perpendicular direction. And then we also may observe some even dynamical tides in such a system. So generally, to sum up my answer, yes, even if the configuration of the orbit is completely circular, we still may expect that we will have some tidal interactions modifying the orbital evolution because of, first of all, differential evolution or spin-orbit misalignment. Yeah, and that's all I believe.
Okay, just a follow-up to what you just said. You talked about the beta period being equal to the rotational period, and that implies probably the synchronicity of the spin. So I want to find out if all the synchronous orbits are secular or whether we still have eccentric orbits that are synchronized.
Yes, so the eccentric orbits, of course, they cannot be truly synchronized. They can only be pseudo-synchronized, like we say. So we can observe some pseudo-synchronicity in eccentric systems, but even for such systems, it will not with such systems, we will not avoid for instance, dynamical tides. So yes, the equilibrium tide and its impact on the evolution of orbit will be somehow minimized, but it won't be excluded totally from the evolution, while dynamical tides will still act on the evolution. So yeah, so even if we imagine a binary system, a heartbeat system, let us say, which is pseudo-synchronized, we will still have some additional contribution to the evolution originating from tidally excited oscillations. Because yeah, they will be still excited, they will still modify both the sizes of the orbit and eccentricity. Also, it will affect the rotational rates of both components. Yeah, I mean, the state of pseudo-synchronous rotation is quite tricky and quite funny, actually, because in this state, I mean, this state is defined in such a way that pseudo-synchronous rotation is such a rotation when the net torque, which is exerted on both components, is equal to zero. So if you will integrate the net torque over the orbital cycle, you will just get zero. But it doesn't mean that you don't have tidal interactions. Their net torque is zero. However, still, tidal forces are changing, of course, over the orbital cycle, and moreover, the pseudo-synchronous rotation rate is not equal to the angular rotation rate at periastron. So there is still some difference. That's why this kind of systems are not excluded from the sample of systems with ongoing tidal evolution.
Okay. I will take a few more questions on chat. We need to round up in 4 minutes.
Okay.
So the next question is from Tajuddin, and the question, he's asking about the conditions of conditions in which you get a stable orbit. If I should take it exactly the way you stated it, what are the conditions of an orbit to be stable?
So is this question the follow-up question of these tertiary systems or binary systems?
I think it is from a different person, so probably it's just talking about binary systems.
Yeah. So once again, this is also a very interesting case. So when it comes to the stability, one of the unstable situation we may have is exactly the situation with hard brake phenomenon. So if the periastron passage distance is too small, like in this simulation, for instance, this is the simulation of two massive stars, and as you may see, every periastron passage, the secondary component is definitely too close to the primary one. And that's why some tidal stream is forming in the system and a lot of matter is ejected. So if the binary system is approaching exactly this kind of configuration, the orbit is behaving in a very non-stable manner. So the typical scenarios, the typical future scenario for such a binary system is that the secondary companion probably will submerge into the envelope, and eventually the system will merge into the single star. So so for some of the heartbeat systems, we may expect that a portion of them will end up as mergers, as stellar mergers. But if the distance is large enough, I don't expect another outcome as the synchronization and circularization. So generally, if the distance in periastron is large enough, the typical evolutionary scenario and stability scenario is such that this system will become circular system with synchronized rotation of the components. So the majority of heartbeat systems are perfectly stable. We do not expect any, how to say it, dramatic phenomena going on in these systems. However, in the evolutionary timescales, I have to mention that and many of them will will undergo some mass transfer events. So dynamically, they are stable. I mean, in the current state, they are very stable. But if you will take into account the evolutionary processes, so one of the components will increase its size, will increase its radius because it will become a red giant, for instance. We may expect that in many heartbeat stars, this kind of phenomenon will happen. So we will have some kind of a mass transfer. And then the outcome depends on many parameters and so many things. So it's quite to discuss all of them now. But generally, the question about the stability and about the future of this system is very beautifully summarized in this slide. So yeah, so the future will depend on both masses and geometry of the orbit. And as you may see here, almost in all cases, we don't have examples of simple evolution, which is effectively single. Well, maybe except this case, where we have very wide orbits. But generally, at some point, these components will start to interact. So more or less, the orbit will be destabilized and some kind of mass exchange or severe phenomena will happen. Yeah.
Okay. We may not be able to take other questions, but I will read about two comments written on chat before I hand over to the working package leader to conclude the program. So then the two comments, one by Tajuddin and the other one by Professor Fulvio. So the comment by Tajuddin, I find this presentation interesting as a learner of space science. Please, is there an opportunity to learn more from Piotr or possibly collaboration? Thank you. Then the next comment is by Fulvio, who incidentally is the PI of Fast4Future. He just left the meeting at about 12:57 p.m. That's Nigerian time. And he wrote, "Sorry, I have to leave. Thanks for the presentation on behalf of Fast4Future team." So maybe in a sentence or two, Piotr, if you can just address the comments by Tajuddin, where he asked if there is an opportunity to learn more from you or possibly collaborate with you.
Yes.
Sentence or two. Yeah.
Thank you for both these comments because they are very kind. So I sincerely would like to thank you. Yes, of course, there is always some kind of possibility to cooperate. The question is on which topic. So that's always the question. I think we may be put into the email contact. I would say it will be the easiest way to collaborate somehow. And yeah, there is always some open question when it comes to the observational analysis of this system. So I would definitely need some help. But I think the most convenient way to discuss these details will be through emails. So if you agree, I would recommend to start some conversations via emails, and then we will see if we can find some kind of synergy between our research of our interest in the research. Okay, I would recommend it will be the easiest way.
Okay, thank you.
Thank you very much.
Hope you took note of what he said, and for some other people that may be interested in any possible collaboration.
Yes.
Then I will be handing over to Professor Fibba, Professor of Physics and Astronomy at University of Nigeria, Nsukka, who is the work package leader, is the team leader of work package 3 to round off the program. Over to you, Fimba.
Yeah. Good. Thank you, Christian. And yeah, Professor Poiter, thank you so much for making out time to be in this seminar.
Thank you.
In fact, the presentation was very awesome, and I'm sure that our colleagues and our students have learned a lot from what you presented. So this our Fast4Future program is a long-lasting one. This may not be the end of being with us. So we do hope that anytime we call on you again, that you may find time to be with us. In fact, we enjoyed your presentation, and we expect that we will have more fruitful collaborations with you in the future.
Thank you very much.
On
I
this,
have
on this
exactly the
note,
same hopes, and I just want to say sorry, a simple sorry, because my presentation was definitely too long. So I'm sorry that I had to skip some of the slides.
no, we quite understand. We understand. Thank you so much. Just as I said, we hope that we will collaborate further in the future, because there will be other programs we have in the series that you may be very useful to us. And we hope that anytime we call on you, you will be ready to answer us. So
Thank you
once
so
again,
much.
I thank everybody, especially our students and other researchers that were able to make it to this seminar. And we do hope that probably next month, we will still join again to be part of the activities. So thank you, and may God bless you.
Okay, just a comment. Piotr is Polish, and his name is pronounced as Piotr. That means
Yeah,
Peter, actually in English.
this is very kind of you, Christian, but it's okay. I know that my Slavic name is
Okay, thank you.
is
Thank
quite
you for
difficult to
that.
pronounce. So if you prefer using English language in full of this presentation, Peter will be perfectly fine. Piotr, Peter, anything you want almost.
Okay, so
Thank you.
we've already concluded the program, and we thank you once again for joining, just like Professor Fimba have already stated. So we hope to see you again next time. Thank you.
Thank you so much. We will be in touch though.
Yeah, bye.
Thank you.
Thank you. Have a nice day. Bye-bye.
Have a nice.
Bye, and
Bye-bye.
you too. Yeah.
Bye.